Hello, my name is David Morton, and I'm a professor of neurobiology from the University of Utah School of Medicine. And today we're going to talk about the digestive system. You are what you eat. Now, why do we need a digestive system? What are the things you already knew before coming to watch this very riveting video? You knew that you eat 3 times a day, or if you're a student, once a day, and it's at the Cougar Eat and it's at Taco Bell. And what you do is you put nutrients in your body, and you're going to chew those nutrients and you swallow. Then the next voluntary thing you remember is when you're sitting down checking Facebook on a toilet. What happens in between your mouth and the toilet is what I want to talk about today, because we need the digestive system, because everything that happens between those two movements, eating and sitting, is taking and reclaiming nutrients from this food, and they go to all the 70 trillion cells in your body and make them function. So to cover this, we're going to cover these digestive organs. We're going to start with the oral cavity. Now, here's an illustration that shows the oral cavity, and there's the mandible. And now the mandible moves up and down. This process is called mastication. And in the mandible, the bottom bone, and the maxilla, the top bone, we have these teeth, 16 teeth on both sides. So when you then take food and you put it inside and you start chewing, this process is called mastication. What happens then is we take that pizza and make it smaller pieces of pizza. But it's still pizza. This process is called physical digestion. You're actually taking food, breaking it down to smaller pieces of food, but it's still food. Now, in the oral cavity, we also have these salivary glands. And salivary glands make, as their name implies, saliva. And there's 3 of them. The one right underneath your mandible is called the submandibular gland. It's the largest. Not necessarily the largest, but it makes the most saliva, like over 3/4 of the amount of saliva. It's the gleeking gland. Have you ever done that? You open your mouth and saliva just spits out of your mouth? That's the submandibular gland. The next is the parotid gland that sits right on the outside of the masseter muscle on your jaw. It makes the next amount of increased amount of saliva, and then the sublingual, very tiny ones underneath your tongue, they make a little bit of saliva. Now, what the salivary glands do are twofold. Saliva comes out and it takes these pieces of food and does 2 things. We have chemical digestion and it makes a bolus. Here we have just a schematic of a complex carbohydrate. This could be a starch from something that you ate. And so in this carbohydrate, they're basically these monosaccharides in a chain. And so saliva has within it an enzyme called salivary amylase that it comes and it chemically breaks the bonds, or I should say starts the process of breaking these bonds. We call this chemical digestion. So these are the 2 types of digestion we're going to talk about. Physical, you break food into smaller pieces of food. But chemical digestion, we start breaking the chemical bonds within carbohydrates, proteins, and fats. So the next thing a saliva does is it's going to then surround these pieces of food and it forms a bolus. That's the term that's used. I kind of think of a bolus like a snowball, except it's not like a snowball in December. It's like a snowball in April where you make it and there's all sorts of chunks of stuff inside of it. That is what you end up swallowing that goes down your esophagus. Now, the salivary gland, you make about 1.5 liters of saliva every day. That's about 4.5 cans of soda. That's what it ends up being, is the amount of saliva you make every day, typically. So after this bolus of food has been chewed up and you now swallow, it enters the esophagus. Now, the esophagus, another name, is the gullet. Now, the esophagus is what transports food from the oral cavity down to the stomach. The thing that's interesting about the esophagus is that there is no metabolic changes that occur in the food. It's simply transport. And it's lined the inside by multiple layers of cells. It's called stratified squamous non-keratinized epithelium, so that as food moves down this esophagus from the oral cavity to the stomach, if it scrapes along the side, there's no problems because that rough bolus of food is going to enter the stomach. And that's what we hit next. But how do we get to the stomach? Well, here we have this bolus. The swallowing part is voluntary. And when you do this, when you go and you swallow your own spit, it's kind of neat. Like if you take your hand and you touch your thyroid cartilage, some people call it your Adam's apple right here, and you go and you swallow, you notice it goes up. When that thyroid cartilage goes up, it sets this mechanical event where some cartilage in the back of your throat called the epiglottis covers your airway. And this is what ensures that the food goes down your esophagus and not down your trachea, the windpipe. And then you swallow, and then you think, well, you actually don't have to think at all. It just happens automatically. And now this bolus of food moves through your digestive system under the autonomic nervous system. It is a law unto itself. You do not even have to think about it. And the parasympathetic nervous system is primarily what drives this. So those of you who heard of the sympathetic nervous system, fight or flight, adrenaline rush, parasympathetic nervous system is the rest and digest. And that is what primarily controls digestion. And so what happens is as you swallow, that bolus of food enters the esophagus, and there's this process called peristalsis. That is the process of moving food involuntarily all the way through the digestive system till the very end. And then at the very end, this is where defecation occurs, and that part is voluntary. So we now go back to a voluntary response. So what is peristalsis? Well, I'm going to use an analogy. Peristalsis is like getting toothpaste out of a container. So here we have that toothpaste container, okay? And so what you do is you then squeeze and then you push. And you usually do it at the end. So if you have a good roommate, they'll do this. But the roommates that don't and they do it all in the middle, they're the worst. Forget that because it messes up my analogy. Start at the end and you squeeze and you push and you squeeze and you push and you squeeze and you push. That's how you get toothpaste out. Well, squeezing and pushing. Peristalsis is like getting toothpaste out of a container. Here we have your esophagus and then small and large intestines because they function the same way. You have this muscle that squeezes that bolus. It's called segmentation. And then another layer of muscle that runs the length of the digestive system pushes. So you have a circular squeezing and a longitudinal pushing. So I think of it squishy, squishy, pushy, pushy. And that's how we move this bolus, much like you do squeezing. There's this inner circular layer of muscles, pushing this outer longitudinal layer, and that's how we move the bolus of food and actually toothpaste out of a container. So as the esophagus through peristalsis moves that food, the bolus down, it now enters the stomach. So the stomach is located between the esophagus and then the duodenum, that first part of the small intestine. And so the stomach is that dilated portion between the esophagus and the duodenum. It has multiple functions. One of the functions is that it has these different arrangements of smooth muscle that churn that bolus. And that you have these types of cells called goblet cells that secrete mucus, and mucus lines the inside of the stomach. Mucus, think snot. Very similar. And then there's also these other cells called parietal cells that secrete hydrochloric acid. And so the pH of your body is fairly neutral at 7.4. The pH of your stomach is anywhere between 1.5 and 2. It's extremely acidic. And so the acid mixes with that bolus, and then the stomach churns, and what do you get? You end up getting this liquidy bolus that is called chyme, C-H-Y-M-E. Now, what does chyme look like? Vomit. Last time you vomited, that's what chyme looks like. But it's this liquidy broken down bolus that then spreads out these tiny molecules to increase the chances of separating smaller particles, so it's easier for the pancreas, we'll talk about in a minute, to chemically digest all those nutrients from your food. The stomach also helps with the reabsorption of vitamin B12 that is initiated in the stomach, and if you do not have that occurring when your chief cells secrete this factor that helps with the reabsorption of vitamin B12, then you'll be deficient in that vitamin. And why do we have this acidic environment? Just think of the next time, if you put it in this context, it's kind of gross, but think of going to the restroom and you walk in and you do your business and then you go wash your hands and you walk out and you touch the door, which has been touched by maybe 4 or 5 other people that did not wash their hands. And so now you've got stuff on your hands and you walk and you pick up an apple and you go, so on that apple are now germs. Those germs have now entered your oral cavity and you swallowed them. And you're now in this dark, warm, moist environment. Germs love that. By the time that hits your stomach, it is one of the key places that helps to stop that type of germs from entering and going throughout the body. However, if you have individuals that they do not produce hydrochloric acid in the amounts that they need to, that it increases their risk for having inflammation in the stomach. All right, so that's the stomach. Now, the stomach is now going to then send food. Oh, stomach. I didn't even have my label in there. That's the stomach. All right, so here we have a cross-section through part of the stomach in that yellow line that now opens, and you can see the inside lining of the stomach that has these irregular ridges that are called gastric for stomach and rugae for folds. Think of it, the gastric rugae look like a corrugated roof, the corrugated metal. That increases the surface area for spreading. And so that little diagram shows so that if you eat lunch, the stomach doesn't go too big because you just had a sandwich and an apple. Do you go to an all-you-can-eat buffet? Then what's going to happen is you're going to have 1.5 liters is the size that the stomach can expand to, which fills a good part of your abdomen because you've just consumed a lot of food. So the stomach can stretch, and those gastric rugae allow it to do that. So the next is the small intestines, and they're called the small intestines not because of the length, but because of the luminal diameter. Small intestines can be about 3.5 times the length of your body. So I'm like 6 foot, I'm 6 foot and change. So you think that I'm going to be somewhere, my small intestines, like 25 to 28 feet long. But again, it's called small because the lumen is narrow compared to the large intestine. And the small intestine has 3 parts. The duodenum is the first part, jejunum is second, and ileum is third. Let's talk about the duodenum first. There are 4 parts within the duodenum. The part that I wanted to mention is that part where it says the second part. And within that second part, it receives all of the bile from the liver and gallbladder and the enzymes from the pancreas. It's going to enter that second part of the duodenum, and that's where chemical digestion is going to start to occur. The next part is the jejunum and ileum. The whole purpose of the jejunum and ileum is for the reabsorption of nutrients, where the chemical digestion just started and initiated in the duodenum. I'll come back to that because I'm going to talk about accessory digestive organs soon, and the pancreas is one of them. So the pancreas will start initiating the chemical digestion, and the jejunum and ileum, their whole goal is to reabsorb and bring those nutrients into the bloodstream. So the jejunum, it's located in the upper left quadrant. That's primarily the part of the small intestine located there. And when you open it up, this isn't a pretty primitive picture. I drew this in graduate school, but the premise was to show those circular folds. They have these irregular ridges, or plicae circularis is the fancy way of saying this. That's what increases surface area for absorption of amino acids, fats, and carbohydrates. Then the ileum is located in the lower right quadrant, and there are fewer circular folds. There are still circular folds, but there's fewer of them. And so if we show then, if we take these parts of the small intestine and look at this barium swallow. So this is an X-ray of the abdomen. And what a barium swallow is you take barium, this chalky substance, and swallow it, and it enters down your oral cavity, esophagus, stomach, and throughout the small intestines. You see this dilated portion that the arrow is showing up here. That is showing the stomach. And as the stomach comes out, there's this thickening called the pyloric sphincter that helps to keep contents from the stomach and the duodenum separate. But then there's the duodenum, and you look at this very velvety appearance. I actually find it quite pretty because the velvety appearance, the feathery appearance is showing those circular folds. And as we go to the bottom right, you see fewer circular folds because that's now down in the ileum. So you get an idea of what the inside, this is the negative space that is shown in this X-ray of what the jejunum and ileum look like. So small intestines reabsorb or absorb all those nutrients. Now the food goes into the large intestines, also known as the colon. Now it gets its name because of how wide the luminal diameter is. So the large intestines are only about 5 feet long. but they're called large intestines because they're wide. And when we look at this picture, there's some very characteristic features that make it the large intestine. One, it looks like almost like a picture frame, not closed picture frame, but it frames the abdomen. You also have here these pouches that are called haustra, very characteristic of large intestine. This long muscle is called the tinea coli, and that long muscle is a thickening of that longitudinal layer of muscles for peristalsis to help push food through. And then you've got these little fatty deposits called epiploic appendages. All those three things are very characteristic of the large intestine. Now, the beginning of the large intestine is called the cecum. Cecum means a blind pouch. It's a blind-ended pouch. That's basically the start. It's the part of the large intestine that communicates with the ileum, and right between them is a little valve called the ileocecal valve. Hanging off the cecum is the appendix, sometimes called the vermiform appendix, which means worm-like appendage. And it's called the appendix because it just means, hey, what is that? It's something that's hanging off the cecum. It's an appendage, so they call it the appendix. Most textbooks would say that the appendix has no function. Now, there's some other pretty cool journal articles that are showing that the appendix may have some functionality in the lymphatic system. For all intents and purposes, really doesn't do anything that we know of right now. A case in point, if it becomes inflamed and you have appendicitis, itis is inflammation of the appendix, and it swells, then that is something that surgically is removed, because if it bursts, then the fecal matter and the microbial biome will then spread inside the peritoneal cavity and get peritonitis, and that is a medical emergency. So when they remove it, people do just fine. There's nothing that they are lost with regards to digestive system or functionality. And the way that it's found is if you feel your belly button, a little tickles when you do that, and you have a bony sticky outie in the bottom right quadrant of your abdomen, right by the belt line or pant or skirt line. And if you make a connection about 1/3 of the way between the bone and the bottom of your hip up to the belly button, there's this place called McBurney's point. And if you push on it and the appendix is inflamed, that's what's going to help give some very good happy feelings. That was sarcastic. That's where you can definitely feel the pain if there's appendicitis. Now, the next part, this is called the ascending colon. It's called that because the feces within this is going up, hence ascending colon. And food goes up the ascending colon and then curves around the right hepatic flexure to the transverse colon. And it's called that because it goes across in a transverse plane. And then here we have the descending colon, because now food is moving down to this bottom left part of the pelvis, in the pelvic cavity. And this we call the sigmoid colon, because that word sigmoid means S-shaped. And then there is the rectum. And all the way from the cecum, ascending, transverse, descending, sigmoid colon to the rectum, we have this reabsorption of water and salts and vitamins. So that's what's occurring all throughout this. So when that is disrupted, for example, say that there's inflammation of the intestines and you are not able to reabsorb a lot of water, diarrhea is what the feces looks like when not a lot of water was reabsorbed. In contrast, if the large intestine reabsorbs too much water, that's constipation, because now there's too much feces in there. Finally, the anus at the very end of this food tube, from the mouth all the way to the anus, here we have two types of muscles that surround it. And it's a sphincter muscle. Now, what's a sphincter muscle? Do this. And that's a circular muscle. And a sphincter muscle, when it contracts, it goes shing, like that. It just gets smaller. And so what happens is there's these two sphincter muscles. One's called the internal anal sphincter, and one's the external anal sphincter. The internal anal sphincter is composed of smooth muscle. It is involuntary. So when feces starts packing in that rectum and starts putting pressure on that internal anal sphincter, that internal anal sphincter starts relaxing and relaxing and relaxing. And you get the moment where you're like, I've got to excuse myself because I've got to go to number 2. The external anal sphincter is skeletal muscle. It's voluntary. It's what is allowing you to go to the bathroom, number 2, when you voluntarily want to. And that is also that reflex of the combination of relaxing the internal anal sphincter and knowing when to relax and contract the external anal sphincter, we call potty training when we have little children. All right, so now that was like the run of the gut tube from mouth all the way down to anus. Let's now talk about some accessory digestive organs. Let's start with the liver. Now, the liver is located in the upper right quadrant of the abdomen as shown by this yellow arrow. The liver has many functions. It's been attributed to close to 50 different functions that this organ has. With regards to digestion, one of the principal things that the liver will do, well, there's two key things with digestion that I want to talk about with the liver. One is it makes a molecule called bile. Now, bile will emulsify fat. What does that mean? So fat, if you think of it, we'll put it this way. Remember last time you had, say, Sunday pot roast, and you washed the dishes and you put them in the water and you took the dish out and you just see fat all on the top of the water. And you'll usually see them in droplets. They go in circles because what a what a dish detergent will do is it breaks bonds between these fatty globules. And so instead of fat, what fat wants to do in water is make a big ball. Fat is hydrophobic. Its bonds repel water, so fat groups into one big ball. And when you put soap, a detergent, it breaks these bonds. And so instead of one big circle, you now have a bunch of little circles. It's still fat, they're just small. Bile emulsifies fat. That's what it does, like a soap detergent. It takes this fat that you ingested, since our body is mostly water, fat will congeal into one big group, and bile goes poof. I kind of think of like shooting an asteroid. It's a big rock, now it's a bunch of small rocks. That's what we mean by emulsification of fat. It's physical digestion because we still have not broken the bonds between fatty acids and glycerol, just the bonds in breaking fat into smaller pieces. The liver also is where blood anything you ingest will be reabsorbed through the liver. So that includes things like alcohol or medications. So when alcohol is consumed, and alcohol goes from the mouth to the esophagus, stomach, small intestine, so it goes from duodenum and the jejunum, alcohol is reabsorbed and the blood goes immediately to the liver, and the liver then detoxifies blood, which includes alcohol. The more the alcohol is consumed over a long period of time, then that can do damage to the liver, and what it does, you get scar tissue that builds up, and it's called cirrhosis of the liver. Also medications, and so the medication dosages are made sometimes based upon how much the liver will break it down. This is why little kiddos and more geriatric patients get usually smaller dosages because their liver doesn't function like, for example, a 19-year-old young man or young woman where the liver's at the prime of their life. Because a medication will get broken down. It's called the first pass effect. So one of the many reasons to keep our liver healthy is that is what all food that we absorb goes first. When the liver is not functioning, it does a host of problems with digestion, with blood, clotting, immunity, and so forth. All right. The gallbladder. Now, the gallbladder sits right underneath the visceral surface of the liver, and what it does is it stores bile. So the liver makes bile, and then what happens is bile comes from the liver, and bile comes down all the way down this tube, and it hits the part of the duodenum, but there's a sphincter muscle that keeps this opening closed. So bile then backs up, goes into this parking lot we call the gallbladder, and the gallbladder stores and concentrates bile. So that what happens then is when you've eat a meal that's high in fats, and fats enter the duodenum, these cells lining the lumen called enterocytes secrete a molecule called cholecystokinin, which then goes and targets the gallbladder and the liver, causing them to contract and squeeze bile down into the duodenum, and that's where fat is emulsified. The next is the pancreas. Now, the pancreas is about 15 centimeters long. It's deep to the stomach and a very important organ. When I think of the New Testament and Paul talked about the members, where does the hand need the arm, the foot, and does the eye need the hand, I actually always think of the pancreas, even though Paul didn't say it, because it's one of those organs that is extremely important and we can't do without it. In the pancreas, I just drew these yellow circles to try to show what are called acinar glands. It's a funny word. These acinar glands produce digestive enzymes that go down this main pancreatic duct of Wurshung, and these digestive enzymes enter this part of the duodenum. These enzymes help to chemically digest food. And so when we take a look at this close-up, I made the enzymes, I just made a schematic to make them look like scissors. They're not scissors. So my friends in biochemistry, I hope that you're not too put out by this, but I wanted to show this concept of what these digestive enzymes do. So that little pearl necklace thing is a protein. A protein is nothing more than a chain of amino acids. And so what the pancreas will do, will take these pancreatic proteases, and they will then break the chemical bonds between these adjacent amino acids. And so what the pancreas will do is secrete these enzymes that chemically break these bonds, so a protein becomes individual amino acids. Now, where do those amino acids go? They're absorbed by the duodenum and jejunum and ileum, and those amino acids go and they make proteins, because all a protein is a chain of amino acids. So it's like Lego. You build something, you swallow a Lego piece, then the pancreas will break down those Lego pieces, the blood will send those Lego pieces, and then those individual amino acids will go to skeletal muscle and make myosin and actin, proteins that contract muscle. They'll go to the pituitary gland, and those amino acids will make growth hormone or luteinizing hormone or follicle-stimulating hormone that are protein hormones that help do things throughout the body. They'll go to fibroblasts to make collagen that knit our tissues together. So the pancreas chemically digests amino acids. Then you also have these pancreatic amylase enzymes, and they'll take carbohydrates and they will then break the chemical bonds between adjacent monosaccharides, and that's how you get glucose or lactose or galactose and so forth. Glucose is essential because this becomes the fuel of the body. So glucose will be absorbed by the duodenum, jejunum, and ileum, and the bloodstream will send glucose throughout these 70 trillion cells in the body. They take glucose, and that's what makes ATP, and ATP is the energy source. So we kind of think of glucose like coal, and then throughout these processes, cellular respiration in the cells make gasoline. And gasoline is something the body can use. We call it ATP. Whereas you can't take coal and stick it in your car and hope to fuel your car, but you can gasoline. And so glucose is what is converted into ATP, adenosine triphosphate. Now, you have these lipase, and lipase is another enzyme that it takes these triglycerides that you had in whatever fat you consumed, and it chemically breaks the bonds in these to make then fatty acids and glycerol that are also absorbed. They don't go in the bloodstream, they go in the lymphatic system, and then eventually to the circulatory system, and that's what makes the cell membranes in the body. That's what makes steroid hormones like estrogen, testosterone, and aldosterone. And then it's also what is stored in our adipocytes or adipose tissue. All right, so there's our pancreas. And that's what's called its exocrine function. It's what the digestion function it has. But also, I just drew in these orange circles. These orange circles are called pancreatic islets or islets of Langerhans. And they make hormones, the endocrine function of the pancreas, that these hormones like insulin and glucagon go in the bloodstream. Glucagon will target the liver, the hepatocytes, and breaks down glycogen to put glucose in the blood if you start exercising and you need more glucose. Or if you just ate a meal, then these pancreatic islets secrete insulin that float through the blood, and like a key will open a door and allow for glucose to enter the cells. So when you damage these pancreatic islets, like for example in diabetes, then those specifically they're called the beta cells of the pancreatic islets cannot produce insulin, and as a result the key cannot open the doors to the cells of the body, so glucose stays in the bloodstream. And that's why when people who have diabetes are trying to control their blood sugar, they'll prick and sample their blood and see how much glucose is inside their blood to see how much insulin exogenously to take, which means I did my mouth. I didn't mean to do that. They'll inject insulin inside and usually through a fatty part of the body. Insulin then flows throughout the body and lets glucose in the cells. All right. So the pancreas has both digestion functions and insulin functions, or the endocrine functions. Finally, I include the spleen, not because actually the spleen has anything to do with digestion, but its blood supply is part of what happens with the spleen. And the spleen is located in the upper left quadrant, right below the stomach. The spleen stores blood. It also filters blood, especially old red blood cells. So when you have conditions like malaria, what happens is red blood cells get malformed, and when those red blood cells flow through the spleen culls out these malformed red blood cells, but there's so many of them that the spleen gets bigger and bigger and bigger. And so there's this elastic capsule around the spleen, and the spleen can then go from this upper left quadrant all the way down to the belly to the bottom right quadrant at times. All right. So here is one of my very detailed drawings of the digestive system. The oral cavity is where we masticate food, physically break it down, and secrete saliva to initiate the digestion of carbohydrates through the salivary glands and the salivary amylase. That bolus of food then moves down the esophagus through this process of peristalsis into the stomach, where hydrochloric acid starts breaking down some of the, and I didn't say this before, but some of the peptide bonds and initiates protein digestion. And then it has this very low pH or high acidity of about 1.5 to 2 and starts churning the food. That food now, the chyme, enters the duodenum, where the liver makes bile and it's stored in the gallbladder, and that bile emulsifies fat in the duodenum. The pancreas produces and secretes digestive enzymes that target the duodenum to chemically digest carbohydrates, fats, and proteins. And so here, this area, I just wanted to focus, that duodenum, a lot happens in the digestive system, and it's only like 12 inches long. But the liver, the gallbladder, and the pancreas all start influencing the chyme in the duodenum, so that now we've got this initiation of the chemical breakdown of carbohydrates, fats, and amino acids. So the whole rest of the small intestine, think jejunum and ileum, absorption of those nutrients are occurring. That's the small intestine. So amino acids and carbohydrates are absorbed into systemic capillaries, where the fats are absorbed into that green central lacteal, where it enters the lymphatic system. Now, the large intestine, you'll notice it's shorter but much wider. This is where water and vitamins and salts, electrolytes are reabsorbed. So the large intestines, there is again these capillaries, so salts, fats, and fat-soluble vitamins are reabsorbed into systemic circulation. The rectum, which the word rectum just means straight, is the straight portion where feces collects and backs up, putting pressure on the anus. And when finally that you decide to go and have a bowel movement, that's when the external anal sphincter relaxes and you have a bowel movement. So in conclusion, take care of your digestive system, because you are what you eat. The more nutrients that you eat of good carbohydrates, fats, and proteins, that all goes into your body cells. And so if you eat cheap carbohydrates, if you don't have vitamins and nutrients, we then starve our cells. And our spiritual body is much like our physical body, where there's that expression that if you want to talk to God, say a prayer. But if you want God to talk to you, study the scriptures. And by reading the scriptures, I love the phrase, feast upon the words of Christ. And so when we feast upon the words of Christ, those spiritual nutrients enter our spiritual cells and knit themselves into making them strong and healthy. And as we do that in our life, as we eat healthy, and as we spiritually feed our souls, God can help us be healthy and strong. In the name of Jesus Christ, amen.